Hey guys. So Carlos told me that he will be late in 5 minutes, and we can start without him. But are we waiting for more people? Maybe meanwhile, do you have any questions about the previous material? Okay, so let's start, and I think Carlos should be here in a few minutes. Okay, so I want to take a step back from rational functions and talk a bit about basic properties of the abelian group of rational points on elliptic curve. So the first thing, maybe I mentioned it, but it's good to recall. For an elliptic curve over a field K, if I have a field extension of K, then the K rational points are a subgroup of the K of the L rational points of E. I mean, when you look at it, E, when I say E over K, it means that the elliptic curve is defined over K. So so you can write y squared equals x cubed plus ax plus b with a and b in K. So of course, if it is defined over K, then for any field extension L, I can consider. I mean, formally, it's a different object. It's the same equation, but considered over the bigger field L. And the k rational points are simply, I mean, the solution for this equation. So clearly we have a subset inclusion of the k rational points into the L rational points. But I claim that this subset inclusion is in fact a subgroup inclusion. And the reason is that the operation that we have in L, for example, it restricts, I mean, if you take a k rational point in E of k, or maybe if you take 2, then doing P plus Q is solving a bunch of equations that are defined over K. And also the solutions of these equations are elements in K. So when you consider P and Q here and you do P plus Q, you're doing the same thing. So this is why we have actually a subgroup inclusion. Is this point clear? This is important. Okay, so that's the first thing. The second thing, what we will consider mostly is the case where K is a finite field. So let's say it's FQ for some prime power. Q. And then we have an elliptic curve defined over FQ. And remember that we have a kind of a partial order set of all field inclusions. I mean, here at the bottom, you have FP. This is included in all the bigger ones. So in particular in FQ. And FQ is included in, for example, FQ square, but it's also included in FQ cube. But here we don't have a field inclusion. However, if you go high enough, in this case, FQ to the 6, then you do get a field inclusion. And now I mean, of course, at the end of this chain, sits FQ bar, which I remind you, I mean, there are many ways to write it. I write it slightly informally as the union of all FQ to the N. This is a bit of a lie, because I mean, as I said, it is FQ to the, I mean, the union of all these things, but not all of these pieces are subgroup inclusions with the next one, so you need to be a bit more careful. But in any case, I have this partial order set of field inclusions, and I can simply apply E on all of that. And I get that the FP rational points are a subgroup of the FQ rational points, which are, for example, a subgroup of the FQ square rational points, and so on. And this is all contained in the FQ bar rational points. Now, so this is a tower of a billion, well, a subgroup inclusions. Now, of course, each EFQ to the n, the FQ to the n rational points over E. I'm sorry. One thing here is something I cannot do, and this is this EFP. Can anybody say why I cannot consider EFP? I mean the FP rational points over E. Remember, I have a field K. The field K for us in this is FQ, or let's say n is bigger than 1. So FQ is strictly bigger than FP, and I consider E over K, so E over FQ. If I consider E over FQ, I cannot talk about the FP rational points over E. Sorry?
Because of Q will be minimal?
Because, I mean, FQ, let's say n is bigger than 1, so Q is P to some actual power. It's not just P. Then when I say that I have an elliptic curve defined over FQ, it means that the coefficients of the equation A and B are in FQ. And potentially they could be in FQ, but not in FP. Right? Because FQ is strictly bigger than FP. And then I cannot talk about solutions to the equation over FP. I mean, it simply doesn't add up. Okay, so that's an important point. I mean, if you have an elliptic curve defined over FQ or defined over any field, you can only consider rational points on a field extension, but not on a smaller field. Okay, so this should be removed, but yeah.
Yeah, sorry. I think I feel I need to ask this now before we go any further. I looked again at your notes. I didn't look at the video from last week. I looked at your notes, and there's not a clear definition of what you call k-rational points. From one, maybe I missed it, but you always mention k-rational points. For me, you're just I just make the shortcut of just picking points on the elliptic curve, but it's more complex than this, and so I can quickly remind the why.
It's so. Let me put it here. K. This is what I call k-rational points. This is the set of solutions x, y, right? Such that y square equals x cubed plus ax plus b. X and y need to be in k squared, right?
But why is the link with a rational function? Like, why are we calling them rational points?
No, the link to the let me just complete this, and we also have the point at infinity.
Yep.
Okay. The reason for the name is that the main case people typically consider a solution to elliptic curve points is over the rational numbers.
Okay.
So by extension, people call it k rational points or just k points.
Yeah, okay, makes. But we are talking about the point on the elliptic curve with the point at infinity, right?
Yeah. So it's like the k rational points are points on the elliptic curve with coordinates in the field.
Perfect. Thank you.
Okay. So I hope the rest of what I said is clear. And then each of the group of fq to the n rational points is finite, right? And this is, by the way, a reason that we did the classification of finite abelian groups. I mean, now that we have the classification, we know that any of these groups has a canonical form, right? Is a product of cyclic groups or a direct sum of cyclic groups. But I claim that E FQ bar is never finite. So why is that? So take some y0 in FQ bar. Then I can consider the polynomial x cubed plus ax plus b minus y0. Sorry, minus y0 squared. Y0 is now just a constant. And this is a polynomial, let's call it phi. This is a polynomial over FQ bar, right? And over FQ bar, every polynomial has a root. So there is some x0 in FQ bar is such that phi of x0 is 0. And this means that the point x0, y0 will belong to the k rational points, sorry, to the FQ bar rational points on E. And you see, I took any arbitrary y0 with no restriction, and I found a point. So since FQ bar is infinite, so is E of FQ bar. Okay, So that's the third remark. The fourth remark is we want to understand, I mean, each of the finite groups is yes.
Can I ask about the proof? Isn't it a bit like there is infinite number of x0 and one y0 that solves the equation?
Yeah, because for every y0, there is an x0. That's
Yes.
equation. And there are infinitely many y0s because it's fq bar.
Yes, but there is infinitely many y0s because the fq bar is infinite.
Yes.
And because there is infinite number of I don't know, it seems like it is like they refer to each other, infinite number of y0s and the infinity of fq bar refers to each other. So I can't understand how we make the conclusion.
So what I need to show you is that there are infinitely many solutions to the equation.
Yeah,
Right?
but
If I show you this, then I prove my claim, right?
yes.
So now I fix y0. For every y0 that I fix, I find a solution. I find a solution I find a root for phi, right?
Yes, but can it be the case that fq bar is infinite, but there is not infinite amount of solutions, or it depends on the equation?
I'm trying to, no, it doesn't depend on the equation. It's always true. So I'm trying to explain. For every y0, I can find a root of phi, right?
Right.
A root of phi is some x0 in fq bar, right? That nullifies phi. But if you then take x0 comma y0, then they constitute a k rational point. I mean, an fq bar rational point.
All right, this makes sense.
Okay, and I can do it for any y0. I can find x0 such that x0 and y0 is a fq bar rational point. They are all distinct points because if you take y0 and y0 prime that are different, then even if the x0 is the same, then the y0 and y0 prime are different. So right. So if you take y0 prime, potentially, well, it has some. I mean, then phi has some root x0 prime. Potentially, x0 prime is the same as x0, but I don't care. As long as y0 is different than y0 prime, then these 2 points are different.
Yes, right, makes sense. Thank you.
Okay, so if you give me infinitely many y0s, and I am over fq, so I can always find a root to phi, then I can find infinitely many points on EFQ bar. Okay. Lisa?
Yes, thank you.
Okay. All right. So what are the points of order 2 in E of FQ bar? remember, for an abelian group, a point of order 2 is a point that if you add it to itself, you get 0. Nicholas, I can try to read, but
No, sorry, I was just reacting to another comment. It's okay, no worries. It doesn't have any meaningful.
yeah. So a point of order 2, it means some p in fq bar, sorry, in E of fq bar, such that 2p is equal to 0. Now, remember, we had a definition when how to define p plus p. To define p plus p, we need to take the tangent. This is in the real case. We need to take the tangent to p, and it intersects with another point on the curve, just one other point. We can call it p star p, and we reflect. We get the definition of p plus p. Now, to say that 2p is equal to O, it means that this point, p star p, or rather this point, is the point at infinity. So 2p is equal to 0 if and only if the tangent to E at P is vertical. And these are precisely the points here, and potentially if I had like another circle, then these 2 points are also with a vertical tangent line. Right, and then I mean, if you take P here, then the tangent line intersects only the point at infinity. You reflect, you get still the point at infinity. You get that P plus P is equal to. Yes.
One question. So the tangent needs to be vertical at P or at 2P?
At P, and then 2P will be 0.
Okay. Now, thanks. Thank you.
Okay, we are looking. I want to understand. This is the kind of baby case. I want to understand all the points of order 2. So I claim that points of order 2 have a vertical tangent line. They must have, right? Because when you do P plus P, you take the tangent line and you look for the intersection of the tangent line with the curve. If it intersects in an actual point on the curve, not the point at infinity, in like a finite point, then P plus P will never be 0. The only way that P plus P will be 0 is if the tangent line doesn't intersect the curve. Doesn't intersect the curve at a finite point. And then we say that it intersects the curve at the point at infinity, and then 2p is defined to be O. This is, of course, only for the drawing is only for psychological reasons. whatever I said here is meaningful over any field. And we indeed define the tangent line and what is a vertical tangent line over any field. So 2p is equal to 0 if and only if the y coordinate of p is 0. Okay, that's the only way that the tangent line at p will be 0. Now, I put it in the equation. And I substitute y equals 0, so x0 is a root of what we called S, or S of E, this cubic polynomial, x cubed plus ax plus b, over, of course, over the field we work. I mean, we now actually, we look for points of order 2 over FQ bar, right? So, you look for, I mean, the points of order 2, they must satisfy, I mean, they must be of the form x0, comma 0, where x0 is a root of this polynomial over FQ bar. And we know that over FQ bar, this polynomial S has exactly 3 roots. Maybe we call it whatever. So write SE x equals x minus x0, x minus x1, x minus x2, and then the points of order 2 this is denoted as E brackets 2. This is the set, I mean, of course, the point at infinity is of order 2. And we have 3 others, which are x0, comma 0, x1, comma 0, and x2, comma 0. Okay, now, in fact, E2 is a subgroup of EFQ bar, because if you add 2 points of order 2, you get another point of order 2. Okay, so we can ask, I mean, this is a group in itself, and by the classification of finite abelian groups, we know that it can be isomorphic to there are just 2 options. One of them is, of course, integers modulo 4. there are simply only two abelian groups of order 4. One is integers modulo 4, and the other is integers modulo 2 direct sum with integers modulo 2. Okay, and in fact, we will see that that E2 is the latter, is isomorphic, always isomorphic to this group. This is called, by the way, the Klein group. Yes.
Sorry, one question. Can you repeat what exactly is a point of order 2? I think I didn't get that.
So this, in general, for any group, and an element in a group, the order of the element is the minimal integer, the minimal natural number, such that if you add the point to itself this many times, you get 0.
Ah, okay.
Okay, so points of order 2 is simply the points that if you add them, I mean, to themselves 2 times, you get 0.
Is that the characteristic of a field?
No, I mean, the character, okay, you can say that if you are given a field, you can look at you can extract from it the abelian group with respect to addition. And then the characteristic of the field can be defined as the order of 1.
Ah, okay.
Okay, so because the characteristic of the field is the minimal number, such that if the minimal integer n, such that if you do 1 + 1 + 1 n times, you get 0.
I see. Okay, thanks.
So, yeah. But more generally, we will want to consider the points of order n in FQ bar, sorry, in E of FQ bar. Points of order n. Now, note that, of course, I could consider points of order 2 in one of the intermediate finite groups, right? I mean, I can always consider the collection of points of order 2 in any abelian group. But in FQ bar, I get the complete picture, right? I mean, here in this drawing that is over R, it could be that this circle does not exist, and then I don't have I mean, I don't have these points on the curve. But if I go to the algebraic closure of R, namely the complex number, I will always have 2 other points. So it is nicer to look at points of order 2 in the kind of the ideal setup. That's the algebraic closure. Okay, so this is just a little bit about the structure, the group structure, and things related to it. Are there any questions about the basic group structure of rational points. All right, so less time. We talked about two things. We said, so again, the setup is E, an elliptic curve defined over field K. And we talked about polynomials. We denoted it as K square brackets E. This is this is what we want to think about as polynomials over E. That is, I take polynomials in two variables, and I mod out by the polynomial phi. Let's say phi is x cubed plus ax plus b minus y squared. And to say that I mod out, I told you that it is analogous to mod phi arithmetic that we had in one variable. But the analogy, you should take it with a grain of salt, because in the case of one variable, let's say kx over a polynomial phi x, we could do like actual long division. I mean, to find out what is what does a polynomial fx looks like in the quotient kx over phi x. We could do a long division. I mean, we could say, okay, fx is some q phi plus r, and then fx is in fact equal to rx in the quotient kx modulo phi. And when we talked about equivalence relations, we said that this is the same as saying that we can define an equivalence relation on polynomials with one variable by saying f is equivalent to g if and only if f minus g, well, if phi divides f minus g, and of course, to say that phi divides f minus g, or actually, if I want to keep the notation, I should say f minus r. Right, and you can see that if I have long division, then to do long division is the same as to do, I mean, to define this equivalence relation and to mod out by the equivalence relation. Now, in the case of polynomials in two variables, I don't have long division. I mean, there are some candidates for long division, but you never get uniqueness. Uniqueness of the remainder and uniqueness of the quotient. So it's not well defined, and I here in the case of two variables, I could not do this one. But equivalence relations are a much more general notion, and they do apply here. So when I say KE is a KXY modulo phi, I really mean that I take KXY times itself, and I mod out by an equivalence relation, which is fxy is equivalent to rxy if and only if f minus r is divisible by phi. And divisibility is a notion that does apply for polynomials into variables, right? You can say, for example, that x minus y divides x minus y times x plus y. Okay, so this is just a warning. We cannot do long division in polynomials into variables, but we can still define an equivalence relation, and this is the analog of the one variable case. Okay, so this is polynomials in E. Now, of course, we can view, so if let's say if k is equal to r, but no, if f is a polynomial over E, well, if it's a polynomial over k, then it defines a function from k squared into k. Right? You simply take a point in k squared, you substitute it in the polynomial, you get an element in k. So if k is equal to r, you can really view a polynomial in two variables as an actual function that goes from the two-dimensional plane to the one-dimensional line. Now, if I have a polynomial in K of E, I can still view it as a function. In fact, I can view it as a function. Just a minute. I can view it as a function that is defined on E. So if you have this curve, then now I can simply look at the polynomial as giving value only on the purple line, and then you get a bunch of points here. Okay, so and in general, of course, this does not depend on the fact that we are in R. F in K of E defines an actual function from the finite K rational points to K, simply by substitution. Yes. There was a question? Nicholas?
Yes, sorry. A little bit above, you're saying we can always define a function on two variables to be to go on to k and not k square. I mean k of x and y. But is it always true? Like, can we always substitute one variable with your, like for example, y square plus yx? You still it's like a general result. We can always substitute one for the other. I can always express y equals something in only x and substitute in the original polynomials. I'm surprised by this. Just
I mean, I say that I'm not sure what you're asking, but if I have a polynomial over E, this is, I mean, I can interpret it, my claim is that I can interpret it as an actual function from E. This is E, or the finite rational points on E, into the ground field. How do I do this? Okay, I have this I mean, I take a point, P, and I plug it in, I take f of P. Right? This I can always do. I mean, P has some coordinates, x0, y0.
you just evaluate it, yeah.
I just evaluate, okay? So I can, and the equivalence relation on K of E guarantees that if F is equivalent to G, then, and P is a rational point over E, then F of P is in fact equal to G of P. Okay, so this definition does not depend on the representative that I choose.
Okay.
Okay, and okay, so this is for the polynomials, right? So in other words, a general polynomial in two variables, it gives you a function from the whole affine space. In this case, and this would be R2 into the ground field, and a polynomial over E is, you can think of it as like a restriction of a polynomial on the affine plane, restricted to the curve, the affine, well, the affine part of the curve. I mean, all the finite k rational points of the curve. Okay, so these are actual functions. I mean, you can think of them as actual functions, although much of what we do is treating them as formal symbols. Now, we also defined the rational functions on E. The rational functions is, I take now K of E, product with itself, but in the second coordinate, I do not allow the zero polynomial. And I mod out by an equivalence relation that is defined as, I take a pair, FG, and I say that it's equivalent to F prime. This FG should be viewed as what I want to consider as F modulo G. And this is equivalent to F prime G prime if and only if, this is a definition, F times G prime is equal to F prime G, but this equality, again, this is in K in polynomials over E. Right? So, in other words, if you want just to look at them as polynomials in two variables, then they are equal in K of E if and only if f g prime minus f prime g is divisible by phi. Okay? So this is the rational functions on E. And the rational functions on E, we said that it's not exactly a function given some rational function. We don't have an actual function from the affine plane to the ground field. The ground field is just the affine line. So this is sometimes denoted as dotted arrow. Okay, so this is like a partial function. But what are my problems? My problems are, R is a regular actually here I wanted to say, of course, we do rational functions on E that's like partial functions on the K rational points of E. And a given rational function is regular at P if there exists a representation R equals F modulo G such that a G of P is non-zero. And of course, for if I take a rational function R, and I know it is regular at some point, I know it is regular at a point P, then I can define R of P as simply you take this representation for which the denominator does not vanish, and you define R of P as this quotient. It could be zero, but if FP vanishes, then it would be zero, but it would always be defined, or always be a number, an element in K. But now we can say if R is not regular, then I simply define R of P to be infinity. And this gives me an actual function, which I also call R. It goes from the finite rational points. Now, instead of the affine line, I now take the projective line. The projective line, I remind you, is just K. One way to represent it is just K plus an additional point at infinity. Okay, so this is a way to to extend the definition to get an actual function. But what we're missing is how to define the function at the point at infinity. And this is what I started to talk about last time, but I will get back to it this time. So before we take a break, any questions on this? Yes.
Maybe I misunderstood what f and g are, because I'm surprised R of p is in k. I mean, R of p is just is 2 coordinates, right?
R is a polynomial in 2 variables.
Yeah.
And P is a point, like a finite point on E, so it has 2 coordinates, x0 and y0.
Oh yeah, so just evaluate it and you get one element in K. Okay.
Yeah.
And my other question is on the projective stuff. I admit I didn't follow this part. How do you define the projective?
Yeah, so the projective line, P1, it should be denoted P1K, it depends on the field. You take the set of, you take K square, and you mod out by an equivalence relation that says that x, y is equivalent to lambda x, y, or lambda x, lambda y, for any non-zero lambda in K. And the equivalence class we denote as x dot y, x colon y, where of course sorry, here I should have said it's like it's k square minus the origin. Modulo this equivalence relation. And we represent a point on the projective line as having 2 coordinates, x, y, but you can, since I removed the origin, it cannot be that both x and y are 0. So if y is non-zero, we can say, if y is non-zero, then x, y is going to be equal to x over y 1, right?
Yeah.
And by that, you get all the points in K. Okay? And if y is equal to 0, then I get 1 point. X comma 0 is going to be equal to x prime comma 0 for any non-zero x prime.
Yep.
Okay, so what I'm saying is these are called the finite points, or the affine. The affine or finite points in the projective line, and then I have just one additional point, which I call, this is the point at infinity. So I can represent the projective line as just all the elements in K plus an additional point infinity.
Wait, why x, the last x 0 is the point of infinity? I thought you could say you can list out all the x's because they're.
No, but you will get equality here because, if x and x prime are non-zero elements, then there exists a lambda.
Yeah.
that, I mean, they differ by a factor of lambda, for some lambda.
Sure, but why is it the point at infinity now?
So this is just a terminology, but it is, I'm saying like, here I get a collection of points. I mean, when y is different than 0,
Yeah.
I get a collection of points that is in one-to-one correspondence to all the elements in the field.
Yep.
Okay? And in the case y equals 0, I get only 1 point. There could be only 1 point with the y coordinate equal to 0.
Okay, so you're defining it as the point at infinity.
Yeah, so I call it the point at infinity. Yes. Okay. And this is compatible with this homogenization of polynomials that we discussed. I mean, essentially, what we're doing here, A1 it can be embedded in P1 by sending a point X into X colon 1. Like this is the affine representation of the point in P1. And this doesn't cover, of course, this doesn't cover the point at infinity. Okay. So in fact, I can look at a rational function as an actual function, but when I modify the range to be, instead of k, to be P1. But to get the complete picture, I would want to define the rational function on the point O. Okay? Because this is the kind of natural thing to do. If I anyway modify the range to be projective, then I might as well modify the domain to be the projective. I mean, the projective version of the curve, namely the one including the point at infinity. Okay? So let's take a 10 minutes break and we come back to define this. Can we start again?
Yep. Let's go.
All right. So we're now in the business of taking a rational function on E. We want to define the value of R at the point O, at the point at infinity. So, I mean, I can, of course, I can write down the definition quickly, but I want to motivate it, and the motivation is, I mean, what do we do in one variable? In one variable, I have, let's say, a rational function with a representation fx modulo gx, and let's say that g of x0 is e0. Then what I look, I mean, e.g., I have some examples in the notes. R of x is x modulo x squared modulo x plus 1. Then x0 equals -1 is a point in which the denominator vanishes. So in order to determine what I want to call R of x0, I divide both the numerator and the denominator by the highest monomial. So in this case, it will be x squared. We get here x modulo x squared plus 1 modulo x squared, which is, of course, 1 over x plus 1 over x squared. And then I can substitute. I mean, sorry, I have, yeah. Oh, I apologize. We want to evaluate at infinity, right? So I mean, I could also define it in a point in which the denominator vanishes, but I want I want to see what we do in the one variable case when we substitute infinity. So I write Rx is equal to x squared modulo x squared divided by x divided by modulus by x squared plus 1 over x squared. And then if the ground field is the real numbers, then I can say this is 1 divided by 1 over x plus 1 over x squared. And when x tends to infinity, 1 over x tends to 0. And 1 over x squared also tends to 0. So I get 0 plus 0. 1 over 0 plus 0 is infinity. So I would define R at infinity to be 1 over 0, which is infinity. Now, on the other hand, let's say I take the rational function in one variable to be x divided by x squared plus 1. Then, and I want R at infinity. I do the same thing. I mean, I write Rx as I divide by the highest monomial. So x divided by x squared. Modulo x squared divided by x squared plus 1 divided by x squared. This is 1 over x divided by 1 plus 1 over x squared. And when x tends to infinity, the numerator tends to 0, and the denominator tends to 1. So I get R at infinity is equal to 0 divided by 1 plus 0, which is 0. Yes.
Yeah, sorry, madam. One question. I know because last time you said that we don't really do L'Hopital. We don't apply L'Hopital because, I don't know, this has some property which we might not be able to follow, or
No, I mean,
because we don't want to explain it.
maybe I misspoken, or maybe you misheard me, but back in the last session, I think I did say that in the case of real numbers, this is L'Hopital.
Okay. Then I misunderstood, or I misheard you. Yeah, my bad.
Yeah, whatever it is. I mean, in the case of real numbers, what I'm doing here, I'm explaining L'Hopital in kind of simple terms.
Yeah.
But of course, we are interested in the general case. I mean, where the field might be just some finite field. So, but we take this analogy from the real numbers, and we take it as a definition. This is another kind of leap of faith that things are going to sort out if we just imitate the case of real numbers.
But is this something that like is proven to be correct that you can do in our particular case, or
I mean,
remains unknown?
It's a definition. I will give you a definition. So a definition does not need any proof. What needs to be proven is that if you use this definition for some kind of statement, I mean, if you then claim that whatever, some object satisfy this definition, then you need to prove it.
Okay, fair enough. Fair enough.
So how do we extract a definition from this setup? What's going on is I mean, in the first case, we had a polynomial of degree 2 divided by a polynomial of degree 1. So, like intuitively, you could say, I mean, the degree 2 tends to infinity faster than degree 1 polynomial. So if the degree of the numerator is bigger than the degree of the denominator, then I would want to say that at infinity this rational function is infinity. And the second case is the opposite. The second case, I have a degree 1 polynomial and divided by a degree 2 polynomial. So when I evaluate it at infinity, it will be I mean, it will be 0, right? Because the degree 2 polynomial tends to infinity faster than the degree 1 polynomial. And what happens in the case of polynomials of equal degree? If R is, let's say, x squared plus 2 divided by 3x squared plus 4x plus 1. Now, again, I do the same trick. I want to evaluate R at infinity. So I do this L'Hopital trick. I divide by the highest monomial, let's say x squared. And here I get 3 plus 4 over x plus 1 over x squared. And when x tends to infinity, this I get 1 plus 0, and in the denominator I get 3 plus 0 plus 0. So this is equal to 1/3. In other words, when the degree when the degree of the numerator and the denominator is equal, I simply take the coefficient of the highest monomial in the numerator, and I divide it by the coefficient of the highest monomial in the denominator, and that's my answer. Okay, so this is in the one variable case. Now, what do we do in K of E? K of E, I remind you, it's like quotients of polynomials that are both polynomials over E. So if I want to evaluate R at infinity, at O, then I need a notion of degree. And the notion of degree for polynomials over E is a bit more involved than just an ordinary degree of polynomials in two variables. Namely, the degree of F for F in K of E. Okay, but in K of E, we have a relation. I mean, in E, y squared is equal to x cubed plus ax plus b. So I would want to say that the degree relation between the x variable and the y variable is 2/3. And if the degree relation between the x variable and the y variable is 2/3, then I might as well say that so we want, or we set the degree of the polynomial y to be 3, and the degree of the polynomial x to be 2. Okay, and if you set up this, then indeed the degree of this polynomial is equal to the degree of this polynomial. And then we can define for a polynomial over E in canonical form. Let's say fxy is some vx plus y wx. And now I have all the components. I can define the degree of f to be, I mean, how do we define the degree of a polynomial that is a sum of two things? It's the maximum of the degree of each of the summons. So the degree of v, v is just a polynomial in x. So I take the ordinary degree of v as a polynomial in x, and I multiply it by 2, because remember, I want to consider that the degree of x is 2. And the other summand is 3 plus 2 times the degree of the polynomial w as an ordinary polynomial in one variable. Okay, so this is a definition of degree that is reasonable in our context. I mean, because we have this this relation on E. But now that I have the notion of degree, I can do what I did. I mean, I can define R of O just as I did in the one variable case. So for R, a rational function on E, maybe I write it in some representation. This will not depend on the representation. Distinguish 3 cases. The first case is that the degree of f is smaller than the degree of g. Remember, f and g are polynomials over E. If the degree of f is smaller than the degree of g, we define R at the point at infinity to be infinity. Sorry, to be 0. If, on the other hand, the degree of g is smaller than the degree of f, maybe I write it like this: degree of f is bigger than the degree of g. And then I define R of O to be infinity. This is in the projective line. And Actually, I have 4 cases, not 3. Or maybe, yeah, 3 cases, but 2 cases here. If the degree of f is equal to the degree of g, then I need to distinguish between 2 cases. Basically, if this degree is even, if this degree is even, remember, by our definition of degree, if the degree of a polynomial over E is even, it means that the highest monomial does not involve the variable y. Right? It is, I mean, it is some x, to the power, to some power. So then I set then the highest monomial of f and the highest monomial of g are of this form. Then I know what I need to do. I mean, then if I do this L'Hopital procedure, I divide by x to the n, everything vanishes apart from the coefficients of the highest monomials. We define R of O to simply be A over B. And if the degree of f, which again we assume is equal to the degree of g, is odd, it means that the highest monomial involves y. So let's say ax to the n y, bx to the n y are the highest monomials of f and g respectively. I define R of O to be A over B. Okay? So, now we have defined, we have defined the value of a rational function at the point at infinity. It could be an element in the field, but it could be infinity. So what I get is that I now have a full definition for the induced function of a rational function on E as an actual function on the k rational points into the projective line. Is this clear? This is it's a bit tricky, but I think it is straightforward. Maybe we do an example of this.
One question regarding this last thing. So to like the conclusion that it isn't it a function is because you just showed that it's well defined also on the 0 point.
Yeah, I mean, because what I said earlier, I mean, before we already defined, if you give me a rational function, I could have defined it on the finite k rational points into the projective line. That is, I mean, if the value, if you take a point P here, if R is regular at P, you simply send it to R of P. And if R is not regular, this is the regular case. And in the irregular case, you send it to infinity, right? Because P1 is K union some additional point, which we call the point at infinity. Is this clear or no?
Yes, thanks.
Okay, so we already had a definition of you take a rational function, you want to evaluate it at any k rational point which is not the point at infinity, and you get we can map it into some point on the projective line. But to make this picture more nice, we want to define the rational function at the point at infinity, and then we have kind of like the projective the projective curve, or the projective points on the curve mapped into the projective line. And the way to do it is, as I defined, with the motivation from calculus, L'Hopital rule, and so on, but with this caveat that we need to define the degree of a polynomial over E in a slightly more involved way, but I guess also something that is very natural coming from the relation that E presents. Okay, so let's do an example. I take, I guess we can say the real numbers, and Rxy, and my equation is the usual, so E is y squared equals x cubed plus 8x plus b, and Rxy is the following quotient: x cubed plus 2x plus y plus 2x to the 4 y divided by x plus x cubed, sorry, x squared plus 5xy cubed. This is a legitimate rational function on E. We can write Rxy equals x cubed plus 2x plus y 1 plus 2x to the 4 divided by x plus x squared plus y 5x to the 4 plus 5a x squared plus 5b x. Yeah.
Yeah, sorry. How can when you define r x of y the first time, how can you say that it belongs to the polynomials modulo the curve equation here, because you have x4 and y cubes?
I didn't say it is in canonical form.
Okay.
It is, I mean, rational functions can come in different flavors. Of course, we can always transform them into canonical form. But if you look at the definition that I gave, I didn't assume that R is given in canonical form. Right?
Okay.
It was just any quotient, because
Okay.
I mean, for this definition, it doesn't really matter. You simply look at the highest monomial, and that's the only thing you care about.
Okay.
So, but here I rewrote the function by I substituted, instead of y squared in the denominator, I substituted of course x cubed plus ax plus b. Okay, so I did a beginning of transformation into canonical form, but it's still not a canonical form. Or if you wish, I transformed the numerator and denominator separately into canonical form, but it is not the canonical form of the rational function. But anyway, so I can do this this substitution, and now what is the degree of both sides? Here I have in the numerator I have I have two summands, so it's the maximum between the degree of the first is 2 times 3, right? Because the degree of it is an ordinary polynomial is 3. I'm talking about this one. The degree of this polynomial as an ordinary polynomial is 3, but in our convention, the degree of x is, I mean, when I consider it as I mean, over e, the degree of x is 2. So this is 2 times 3. And the other summand, I have 3, because I have y here, plus 2 times 4. Okay, and this is 11. Yes.
Sorry, Matana, I got lost here. So you said that we consider x. So the first monomial, if we see that it as a regular polynomial, this has degree 3, of course. So where's the 2 times?
Because
3?
remember that this goes back.
No, sorry, I didn't ask correctly. So I agree with what you said in the definition, but then in the other side, shouldn't we have 2 times 4 and then times whatever y was? I think 3.
The degree of y is 3, but how
they add. Yeah, my bad.
Okay.
My bad, I'm stupid. Sorry. Yeah, thank you.
No, it's not stupid. I did the same mistake last time, so don't be too hard on yourself.
Thank you.
But what do I have in the denominator? I have 2 times 2. I mean, the maximum between 2 times 2 and 3 plus 2 times 4. So that's also 11. Okay, so now if I want to evaluate R at the point at infinity, like again, it's you can think of it as like I'm doing R, and instead of X and Y, I substitute infinity. But then I go to the formal definition. I look at, so we are in the degree F equals degree G case. And both of them are odd. Okay? So I look at the highest monomial, and I simply divide the coefficients. The highest monomial is, in this case, it will be 2x to the 4 times y. And below I have 5x to the 4y. Right? These are the highest monomials. And then R of O would be simply 2 over 5. Okay? I know it can be a bit confusing at first, but
No, it makes sense. It makes sense.
it makes sense? Okay.
Yeah. Sometimes we do emojis to kind of say that all is good, but maybe you don't see them, Matan, so maybe we should just reply, because otherwise it might be confusing for you, because we sometimes say yeah, but maybe you don't see it. I'll try to say it now.
Yeah, I mean, okay, if somebody says yes, I mean, yeah, indeed, I miss the emojis sometimes. But okay, so this was one step. To tell you what we're heading to, I mean, when I take a rational function, of course, I can say when the rational function has a 0, it means that it's a point on the curve that, so maybe I just write the definition. Fix R a rational function on E for a point P in E of K, or let's say a point P is called a 0 of R if R of P is equal to 0. And a pole of R if R of P is equal to infinity. And what we will be interested in the next few sessions is to understand to what extent the zeros and the poles determine the rational function. It will turn out that they almost completely determine the rational function. And if they almost completely determine the rational function, then I can cook up rational functions by just defining a set of zeros and poles and some additional information. And this will be pivotal in the construction of the well pairing. Yes.
Just one question here. Seeing the definitions that you now give for zeros and poles, this sounds similar to when you do analysis of functions and you define maximums, minimums, and inflection points, because you also need to substitute when you derive and you substitute by zero, you might also need to run L'Hopital for derivating, and you get first and second derivative there, which kind of also helps you to define how a function behaves. Does that have anything to do, like any kind of? It's just similar by chance, or there are things behind the scenes that are connected?
It's a bit. I think you are a bit mixing. What you do in calculus when you look at the maximum and the minimum, these are not zeros and poles. Or you could say they are zeros. I mean, the maximum and the minimum are zeros of the derivative.
Yeah, exactly. Yeah, that's true. That's true.
But apart from this is typically, you don't consider a quotient. So okay, so zeros, yeah, zeros are zeros. You know, that's defined for any function. Poles are only in the case of when you have quotients. And poles, you don't usually use the poles for in ordinary calculus.
Yeah, that's true.
Right? So it's a bit different, but it turns out that the zeros and the poles in our case, and there is, I just didn't want to get into a more analysis, but there is a treatment in analysis of complex numbers or complex functions. There is a lot of use of zeros and poles, and this helps you to classify complex functions of certain kinds. But this, I thought it would be too much of a detour to get into. So for us, I mean, we have a natural notion of zeros and poles of a rational function in our case, and we'll just take it from there.
Fair enough. Makes sense. Thank you.
Yes, Nicolas.
Yeah, sorry, I think I missed a step. Can you go a little bit above? Yeah, here you say R0 equals R infinity infinity. I understand this because the degree are 11 and 11 on both on top and bottom.
No. Here, what I suggest to again, we have formal definitions, but to kind of gather things quickly, it's useful in our cases most of the time to regard O as having two coordinates being infinity.
Okay, and where does the R0 equal 2/5 come from again?
Because then I take the highest monomial in the numerator, I take the highest monomial in the denominator.
Yes.
And I divide the leading coefficients.
But why? So I'm confused. You're looking at the highest monomials and you say R0 equal 2/5. But why was it useful to look at the degree then? I'm sorry.
Because I needed to know, I mean, if the degree of the numerator is bigger than the degree of the denominator, then I want to say that R of O is infinity. Right? Because if the degree of the top is bigger than the degree of the bottom, then the top tends to infinity faster than the bottom.
Yeah, okay. So it's because you have the same degree on top and the bottom that you can say that now I'm looking at the monomials, at the highest monomial.
Exactly. And I needed a notion of degree
Yes.
For the other cases.
Okay.
Or in fact, also for this case. I mean.
Okay. Thanks.
All right. Famous last questions. Then see you next week.
Cheers. Have a nice weekend.
Cheers.